Hello again, dear students. Now I'm here for another section in your chapter 4. Maybe this chapter need more work, so I need your full attention. Please be with me. In case you feel tired, stop or pause the video and start again to see what's going on. Because really any misunderstanding make your work more mistake, make the work more difficult on you. The first part is talking about increasing and decreasing. So you have monotonic function. Monotonic means that at the same, like extrema means that max mean. Monotonic means that increasing and decreasing. Okay, dear, here's the increasing function and decreasing function. So in that case, if you want to find, because we are going to sketching the graph, as I told you, sketching the graph. So for the graph, all of them, graph, we need something, where's increasing, where's decreasing. The function, where is going on to up, where is going on to down. So racing or racing up or racing down, that's the meaning of the increasing. And we have a definition, or the corollary say that if the first derivative is greater than 0 at any point, means that the function is increasing on this interval. Okay, for example, you have a function continuous on this one and differentiable on that one, as we talk about these conditions in the mean value theorem. Now, if the derivative of this function during this period on this interval is greater than 0, means that the increase, okay, increase. And the inverse of this one means that decrease, if the first derivative is less than 0. So how we know about this one is increase or decrease? Now I'll give you the we are clarifying these concepts by the definition. Example 1 in page 10, the section 4.3, we have what? We have the function f of x is equal to x cubed minus 12x minus 5. In that case, if you want to find the increasing or decreasing, you need what? You need the first derivative. Okay, so the first derivative will change to the 3x squared minus 12. Am I right? And if you take a common, as we needed, because I'm going to tell you why we need this one, we have 4. And you know this is the difference between two squares. So we have x minus and x plus. We have 2. So this is the first step that you can do it. Find the first derivative and see whatever or whenever is greater than 0 or less than 0. This one give you increasing and this one give you decreasing. Increasing going to up, decreasing means that going to down. Okay, so how we test this one? We need the essential points. We have minus 2 and 2 here in the first derivative. Okay, we have what? We have minus 2 and 2. You know, if I am going to say this one equal to 0, okay, x plus 2 equal to 0, I get what? X is equal to minus 2. That's why I put the minus 2. If I say x minus 2 equal to 0, I say x is equal to 2. That's why I put the 2. So we'll recall this one as an essential points, or like a critical points. You can say critical points or any other else. So let me C1 and C2, okay? And try to test by the neighborhood points. We need a test points or neighborhood points. So first of all, try to sketch the line. The second, we are choosing the test points. Okay, test point. For example, here's minus 2. Neighborhood for minus 2, I can say minus 3. How about between minus 2 and 2? I'm going to choose 0. How about choosing the value, any value? You can just like choosing like that, because we don't need a mentioning any increasing or decreasing. Okay, so how about the value greater than 2? I am going to choose 3. Up to you. You can put 4, 5, any number. So optional points. Okay, so put these points. Okay, step number 3, put neighborhoods points into factors, or into the first derivative equation, which is a equation star. Okay, here's the equation star. How? So put -3 here. Okay, I have what? I have f of first derivative is equal to 3x minus 2x plus 2. If I put -3 to here, I get what? -3. The important things here is the sign, is not the result. Okay, don't mention the result. I need the sign. So if I put -3 to here, I get what? If I put -3 to here, I get what? -3. I get -5, so minus. If I put -3 here, I get -1, so minus. Minus multiply minus is equal to what? It will be positive. So I'm going to write here as a positive. Okay, the green. So I'm going to write here as a positive. So for the step 3, the third step, I have -2, 2, C1, C2. And here is what is positive. Here's positive. Okay, dear. How about if I put the another value, 0. If I put 0 here, I get what? If I put 0, 0 minus 2 is equal to 0, so means that -2 is equal to minus. If I put 0, I get positive. So positive multiply negative, the result will be negative. How about for the third value? The third value will be 3. If I put 3 here, I get positive, right? I put 3 here. 3 plus -2 is equal to +1, so it means that plus. If I put 3 again, I'm going to get the result will be positive. So positive by positive again will be positive. Okay, positive. So negative, sorry, positive, negative, positive. The negative means that decreasing. The positive means that increasing. Okay, that's all. So means that the function before the -2 increased till -2, the -2 decreased to down, and then again what happened? Again increased. Look, the function increased till -2, then again decreased till we get the number 2. Here's 2, you can see, and then increased after this one. That's why we have what? We have the increase and decrease. That's all about the increasing and decreasing. And you can see this table again. It's the same things. The sign of this is the important part of the table, and this is about the increasing, decreasing, and increasing. Okay, so if it's a positive, increase. If it's a negative, it's decrease. That's all about the first page number 10. Okay, dear. So how about, it's also about the first derivative. We talk about this one, and you see that as a step change, and then if there's a maximum and minimum. Now here we have a maximum and minimum. Look, in this graph, in this before example to the page 11, he see if the f prime change from negative to the positive, so have minimum. If the f prime change to the positive to the negative, you have a maximum. If there is no change, means that there has no local extrema. If you want to find the positive and the maximum and minimum point here, local maximum and local minimum, we say that local. He say that if from the positive change it to the negative, from positive change to negative, means that we have what? We have maximum. Look, here's positive, here's negative. Sorry, negative. So we have what? Change it to the positive, then here directly decreased. So if we have increase, decrease, positive, negative, means that we have local max. And he said that if you have the sign changed from negative to positive, negative to positive means that we have local minimum. And also he said that if there is no change, means that no local, no max, no mean, no local extrema, means that no max, no mean. So in that case, we have what? We have the value changed from the positive, okay, from the positive to negative, means that here in that point we have max, local max. Also, if we have a change from negative to positive, we have local mean, means that, okay dear. So later we will collect all these information. First critical point, second max, mean, then later and concave up and down, and second derivative. Then we can really draw some nice picture like that without any calculation, without any calculator, without any computer. So you can do it. Why? Because you have information about the properties of the function, then you can do it. So this box is talking about positive to negative, means that we have max. Negative to positive means that we have a mean, locally max and locally mean. No change, no local, no change, no local. Means if you have a negative, negative, even at that point we have no local. Positive, positive, we have no local. Okay, that's all. So how about if I have positive, negative, negative, like that? So here we have mean, but here we have nothing. For example, if I have a minus 2, 0, 1. I see between minus we have a minimum, but here we have nothing because nothing happened. Okay, that's all. Now find the critical points or point of the function. We have another example in page 11, example 2. So f of x is equal to x1 over 3 x minus 4. Okay, so first of all, you know, we need to find the derivative. Okay, find the derivative f of prime of x is equal to, directly I'm going to write really this like that, because there's no time for doing the calculation. You can do it at home, and you have the result. I'm going to show you, there's no time for fun. I taught you about the derivative, so you can do it now. This is the time for testing the sign. Do not forget about all these steps together. Now I am combining all of them because you are now expert. You can do it. So we have what's happened if the critical point. What's the important points here? Is the 1, because this will make our function to be 0. And where's the other critical point? So C1. Where's the other critical point? This is the critical point because we say that f prime of C should be equal to 0. So in that case, just x will be 1. How about the other point, about the definition of the critical? I say undefined, which point is 0. So it will be our C2. Please, for finding this one, review the 4.1 and 4.2 together, especially 4.1. So in that case, we have to see two critical point, 1 and 2. Now it's time to find the maximum and minimum, and increasing and decreasing if we have a max or mean, whatever. So now I'm going to choose the point here again. What I have to choose the point. I'm going to choose -1, and I'm going to choose 0.5 between the end, and I'm going to choose also 2 here as a neighborhood points. Half, -1, 2. It's okay. Feel free to choose any point. So if I put minus here, I get what? Minus. The upper will be minus. And if I put minus here, look, here's some square and 3. So every time, because I have this square, every time the denominator will be positive. So I am not testing it again. Just the numerator is important for me in this example, not in the whole the example, in the general case. No, as a special case, because I have a square here, this will make the new denominator to be positive. If I put minus here, I get minus. So negative over positive, it will be negative. And for the other part, for the other value, 0.5, if I put 0.5, again, I am going to get minus 0.5, so it means that again negative. If I put 2, if I put 2, 2 will be positive. So here I will get the positive. So the function here, I can say is decreased, okay, decreased and increased, okay, decrease and increase. At the example, at the test also, you can do the same thing that I made it here. So tell me about the critical, the max extrema points. Tell me about the extrema points, as we mentioned in the page 11. You have a box about the extrema point. So because there is no change, so there is nothing about, because I have a negative, change it to the positive. Look, decrease, change it to the increase. So here we will have what we have at, look, at 1 we have minimum local, minimum. If you don't measure the local, it's okay, minimum, okay. So the minimum point is 1, and put 1 in the function, put 1 in the function, and you get the result, which is equal to minus 3. F of 1 is equal to minus 3. Put in the function, do not forget about that, okay. When we are talking about the point, you should put in the original function. So I didn't say f prime, I say f1 is equal to minus 3. Put it in the 1 cubic root of 1, f of 1, what 1 minus 4, which is equal to minus 3, as you know. So in that case, we have a minimum point here. So the minimum point will be 1 and minus 3. I don't know about the graph really. Why? Because still we need we need more work. But here's the figure that make your imaginary more to be real. Here's the minimum point, but I don't care about the graph here. I care about how to find the critical point and how to highlight the decrease and increase places, and how to find the minimum and maximum point, okay. Okay, here, look at here's the minimum. It mentioned it here in your book, page 12, and here's minus 3, and here's the point you can imagine, okay. That's all about this piece about talking about the maximum and minimum. Now we are going to talk about another part, with another part also help us for preparing about, we are nearly to sketching the maximum point and minimum point, and about the sketching the graph. So we have what, concavity and curve sketching. Before sketching, because the graph or sketching we need something else. We need concavity. Concavity. When I say concavity, means that concave up and concave down, up and down. So it's a time for finding up and down, concave up or concave down, the curve, okay. So here's the result, and here's the theory about the concavity. Now the definition: concave up is an open interval, f prime increase on r. We don't say f, we say f prime, means that f double dash should be what? F double dash should be positive. So try to use this box This is the summarized all the speech here. So if the f double prime, f double dash, f double prime is greater than 0, means that we have a concave up. If f double prime is less than 0, so means that the value of f double prime is negative, the graph will be concave down, means that the shape will be like that. So here's the example 1. I'm going to solve for you and to clarify for you, because if you wanna understanding this box, really you need the solution of the example. So here's the example. The example 1 in your page 13, section 4.3. Example 1, page 13, section 4.3. You know this, which talking about if f of x, we have a and b. F of x is equal to cubic x. So in that case, how we find the concavity up or down? You know, first of all, we are going to take the x squared, the second, we need the second derivative. Why we need the second derivative? Because the second derivative is going to talk about the concavity, it's up or down. So in that case, we say that 3 is equal to 3x, and we say that 6x will be greater than 0 where, and 6x will be less than 0 where. We need to find this location. If we find the location, means that we know where's concave up, where's the concave down. So you know the second derivative is equal to 6x, then we say 6x will be greater than 0 whenever we divide by 6 both sides, right and left of the inequality will be greater than 0. So in that case, we say if x greater than 0, then second derivative of x, then second derivative will be greater than 0. So where's the x greater than 0? Here, you know, here, right? Even in the equality you can include it here. Here's x greater than 0. So we have, for this one, we have in concave up, you know. We have concave up by what? By the first definition of this box. So if greater than 0, we have a concave up. Do not forget about that. Up means that concave up. Wow. In that case, we have this situation. How about the second case? We see the second case also can be less than 0, then x means that less than 0. In that case, so it's concave down where x is less than 0, so means that concave up here. So it means that we have something like that. Okay, we have something like that. Now there's a summarizing things. Maybe the concave up like that or like that, or maybe concave down like that or like that, or means that like that or like that. So which case of the curve we should select it here? For example, I say less than is equal, less than is concave up, so means that we have like that. Okay, dear, that's all about the first example. How about the second example, or first example, part B? Sorry, about part B. So here we are. Here we are. The part B is equal to so here part by is equal to x squared. You know, first derivative will be 2x, the second derivative will be 2, and you know, usually and every time and whenever you have a x, this one is greater than 0, so it means that the second derivative always is equal to greater than 0. So it means that we have a concave up, means that we have this one and that one. But how? Or this one or that one. But how we mention this one? You know, we have a concave up like that and concave up like that. Okay, dear. So that's all about the first example in page 13. Now I'm going to the fully information page, the page 14 and page 15. I was talking about also point of inflection point. Okay, it's inflection point. Inflection point is another concept that I told you today that we are taking it. You have an inflection point if either you have a two case of inflection point, okay, like in critical point. If the second derivative is equal to 0 or is failed to exist, or means that undefined, okay. So in that case, in both now here in the page 14 we have many things about inflection point, which is very important. The inflection point is what? Is the point that if the second derivative is equal to 0 or does not exist or undefined. In that case, inflection point, and we have an additional condition, the concavity should be changed from the concave up to down. Otherwise, we say we have no inflection point. So, for example, f of x, example 3, the page 14. For example, in that case, we say what? We say we have a concave up or not. We should we should test it. So f of x is equal to x to power 5 over 3. You know, in the first derivative you have 5 over 3 x cube, like that, and the second derivative is equal to 10 over 9 1 over x cube. So in that case, you know, both are positive and negative. Sometimes are positive, sometimes are negative. Okay. So in that case, we see that this is the inflection point or not. The first, where is equal to 0? Nowhere. So is undefined or not? Does not exist? Yes. At what? At x is equal to 0. Second derivative does not exist, right? So we can say at x we undefined. F double prime is undefined, as you know, as you can. You say undefined or does not exist at here. So the second derivative is undefined. Okay, this is the first time. So it's an inflection point, but we should test it. The second derivative changed at 0 or not, at x is equal to 0. Why? Because if at x is equal to 0, the second derivative then change from concave up to down or down to up, it will be a problem. This point will not be the inflection point. So that's why we have what? We should test it. How we test it? You know, if I put positive here, here's the 0, and here's the second derivative. Do not forget about 10, 9, 1 over cubic root of x. So because the cubic, if I put positive here, I will get positive. I put negative here, I will get negative. So this is concave up, this one concave down, and this is the will be inflection point. So yes, as I'm clarifying the idea, we have an example 4, the same page 14, section 4.3. Example 4 say y is equal to x to power 4. You know this function, even the first is equal to 4, the second is equal to 12x square, and at x is equal to 0, we will get second derivative to be 0. But because this is not changeable, positive, so this point is not inflection point. Okay, why? Because there is no concavity. So that's very important. Example 3 and example 4 talking about concavity of the what do you say, of the function, because there's the where the concavity not changed, there is no inflection point. Okay, that the nor second it does not change sign, so no inflection point, has no inflection point there. Okay, also you can see I'm leaving this example for you as a homework, because the same you can see how can the concave up, concave down change it, and there's an inflection point. Okay, because the second derivative changed. Okay, so we have what? We have an inflection point in this example. I'm leaving this one for you. So this theorem, the theorem number 5 in the last change, control or collect all the things that we needed. You see how where we have a local maxima, local minima, you hear this one about the critical point, right? And that's all about the finding the critical point in the second, and you see in the critical point second derivative is less than 0, we have a maximum. Second derivative is greater than 0, we have a minimum. And if what do you see, if the is equal to 0 is equal to 0, the test fails. So this test is not useful every time. We should be more clear. I have an example for you. It's a long example and give you more idea about how to sketching, or how to nearly to sketch the graph. Really, I need your concentration, because very, very important for you. F of x, so example 7 in page 15, section 4.3, very important. In the exam, really you will face something like some example like that. So f of x is equal to x to power 4 minus 4x to power 3 plus 10. So in that case, how we find the concavity up and down? First of all, try to make the function to be 0, because we need a critical point. Okay, here's the strategy in the page 16. Before this one, read this one, then go again to find the page 16, find the what do you say, find the strategy. So find the first derivative, find the first and the second derivative, find the critical and inflection point, and increasing, decreasing, concave up, concave down. And then you can asymptotes also, they are important. You heard about this one in the chapter 3, vertical asymptote, vertical and horizontal asymptote, and slant asymptote. You slope slant asymptote also, they are very important for this subject. So first of all, we have 4x to power 3 minus 12x to power 2. So we will say f prime to be 0. So in that case, I am going to take a 4 as a factor, so I get also x squared, so it remains x minus 3. Am I right? So in that case, f prime is equal to 0, if x equal to 3, or x is equal to 0. So we have what? We have two critical, C1 and C2. Am I right? So try to do this one slowly, because you need more practice. You should be more careful with that example. So we have C1 is equal to 0 and C2 is equal to 3. Now it's time for what? Time for finding the increasing and decreasing part. So in that, we have a first derivative. Do not forget about that. We need the points. Here I am going to take -1, 1, and 4. You know what's the test points, or you can say neighborhoods points. So here f prime will be what? Will be, if I put -1, it's always this one is positive, so minus positive, it will be negative. And if I put 1, positive, negative, so again negative, and if I put 4 positive positive, so means that positive. So now here I have an increasing, decreasing, decreasing, and increasing. Okay, that's all. How about the second example? So the second derivative will be equal to that one, and we will take the, we'll make a second derivative to be 0. So after factoring, we get x is equal to 0, x is equal to 2. So here we have x0, x2. So how about concave up, concave down? I will choose again points like a -1. Here I'm going to choose 1. Here I'm going to choose any number, 3, 4, up to you. You can say also 3. So for concaving up and concaving down. So in that case, if I put if I substitute -1 here, I get minus minus, which means that minus multiply minus positive. And here, if I put 1 here, I will get 1, 1. So 1 positive, 1 minus, positive, negative, I will get negative. Again, I put 3, 3, 3 is positive. So I got him positive here, means that concave up. Okay, here means that concave up. Here means that concave down. Here means that concave up. But I don't know this part or that part. Also, I don't know which part in this concave up and concave down. So I'm collecting the information later. Now it's time to, this is the table 1, the table 2. It's time to collect both informations. As I told you, we will put the all important points like a 0. Okay, what else we have? 2. Look, here's 2. I'm choosing 2, also 3, because this is the last table. Okay, table 3, or that's very important. And I know I have negative, 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 positive. Am I right? Don't say why my teacher changed it to the 3 negative. It's not 3 negative. After 3, less than 3, we have a negative. So, and again, before 3, we have a negative. After 3, we have a positive. You can see. How about here? Before 0, we have positive. So this means that decrease, 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 increase. Okay. How about here? After it's another positive and negative, another meaning. Before 0, we have positive, which means that later I'm saying that. Between 0 and 2, we have negative. And after 2, we have positive. So it means that up, down, up, up. Okay, this is very important, because and you should be careful, because you are copying this one to here and copying this one to here together, and you should put all the important things here. We have 0, 0, critical inflection point. So 0, 0. We have 2 here, inflection. We have 3 here, critical. So we made a mix. We mix all the points here. That's why I say we summarize. After this one, you can really sketch the graph. You know how? You don't know how? Just let me do something else. Let me put the important points in the function. So f of 0. Sorry, f of 0 is equal to what? If I put the 0, I will get, where's the function? Here's the function, f of x is equal to, for example, x to power 4 minus 4x to power 3 plus 10. So if I put 0 here, I will get 10. So the important points 10. If I put 2, I will get what? I will get minus 6. Try to put it here. So 2 and minus 6. It's another important. It's inflection point. If I put 3, I will get minus 17. So 3 and minus 17. That's all. So all these information will make my graph to be visible, to be a real graph, to imagine from the image to draw the graph. Okay, to draw the graph. How? I'm going to show you. here's the x and y axis, right? So the points are, the important points are 0, 2, 3. And how about the points? We have 0 and 10. Okay. 0 and 10. Also we have 2 and minus 6. So 2 and minus 6. Okay. And 3 and minus 17. 3 and minus 17. Okay. So now it's the time of the map. This is our map, important map here. Okay. So how we sketch this? We say we have a concave up, okay, before 0 and decreasing. So the function will come to here, till here, okay. The function will come to here and concave up and decrease. So decrease and up, decrease and up, tell me it's like that, okay. Decrease and up, tell me like that, because this is the decrease and this is the increase. Decrease and increase. So which part I should select? Decrease and concave up. So like one. This one increase, this one decrease. So which should I select in this part? Decrease, and so I should select that part, right? That part. So here's the decrease and concave up. And between 0 and 2, I have a decrease and concave up till 2 and minus 16. So I have what? I have something like that. Am I right? I have something like that. Why? Because it's decrease and up. So this one decrease and up. This one decrease and down. Okay, so you say decrease and up. Sorry. This part is decrease and down. How about the other part? The other part say between 2 and 3, which we have this point, we have decrease and up. So decrease and up. Here's the decrease and up, right? Decrease and up, because the other, sorry. So I made a mistake here, really. These one are up. Sorry. These one are up. These one are up. So I'm going to change, make it here more clear. I have decrease, 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 increase. Okay. Here we have up, down, up, up. So together I have decrease and up. Okay. Decrease and down. Decrease and up. Sorry. Increase and up. Increase and decrease and up. Decreasing and up. And what? And increasing and up again. Increasing and up. Like that. Okay. So that's the special part of the summarized part. Okay. 0, 2, 3, and also. So now between 2 and 3, I have what? I have decrease, decrease and up, like that. Decrease and up. And later, after 3 to 4 and something is, we have a up and increase, increase and up, like that. Okay, dear. So decrease and increase, decrease up, increase up. And you need just a little bit really time to deal with that example, that's all that you need about the example. This is the procedure. Please try to read this one and try to solve the example 8. Okay, or maybe in the next video I'm going to help you to sketch the, what do you say, the example. Bye for now.